Humanity spent thousands of years viewing the cosmos as a stable, predictable system. From a distance, the stars moved with the precision of a clock. We built our understanding of the world on the belief that reality was simple. The Earth felt solid. Objects occupied definite places. Causes produced reliable effects. By the late 19th century, scientists like James Clerk Maxwell had established laws for light and motion. These laws seemed nearly complete. The foundation of physics appeared secure. At the dawn of the 20th century, the universe was widely considered an understandable, machine-like system. That certainty began to crumble when researchers peered inside the atom. Instead of solid building blocks, they found vast empty spaces and electrons that behaved in ways that defied classical logic. The deeper science looked, the more the rules of our everyday reality began to fail. Over the next few decades, quantum mechanics would dismantle our assumptions about the three most basic components of existence: place, objectivity, and distance. Looking inside the atom revealed a landscape that human logic could no longer map. The first assumption to fall was the idea of place. In our daily lives, a particle should always be somewhere specific. Yet quantum mechanics shows that before measurement, an electron does not possess a definite location. Instead, its mathematical description spreads through space as a cloud of possibilities. Remarkably, this strange behavior revives an ancient idea from Aristotle, the distinction between potentiality and actuality. Aristotle argued that a seed contains the potential for a tree, or a block of marble the potential for a statue. For him, possibility was a real, tangible aspect of existence. At its foundational level, the universe functions as an ocean of possibilities, waiting to become actual. This leads to the second challenge, objectivity. If reality is a sea of potential, we have to ask what forces a specific possibility to become real. The double-slit experiment provided the answer. Scientists fired a beam of electrons at a barrier containing two narrow openings. The electron behaves as though it passes through both openings simultaneously, interfering with itself like a wave and creating a complex pattern on the screen behind it. When scientists attempt to observe which slit the electron uses, the wave behavior vanishes. The electron acts like a solid particle, leaving two simple bands. Observation alters the outcome. We cannot separate the observer from the reality being observed. The act of measurement itself transforms potential into the actual. No scientist resisted these subjective conclusions more than Albert Einstein. He argued that the moon should exist whether or not someone is looking at it. Einstein spent decades searching for a deeper explanation to prove that quantum theory was incomplete. Opposing him was Niels Bohr, who argued that the universe is under no obligation to conform to human common sense. Their debates were eventually settled by the discovery of quantum entanglement. When two particles interact, they become linked. Manipulating one particle instantaneously affects the other, even if they are separated by an entire galaxy. Einstein called this spooky action at a distance, as it seemed to defy the limits of space. Entanglement suggests that physical separation and distance may be illusions of perspective, revealing a universe that is far more interconnected than it appears. If matter, objectivity, and distance are not fundamental, we are left to ask what reality actually consists of. The many worlds interpretation proposes reality continuously branches. In this view, the wave function never collapses. Every quantum possibility becomes real in a separate universe. Physicist John Wheeler then proposed a different radical idea, it from bit. Wheeler suggested that physical reality emerges from informational relationships. At its deepest level, existence resembles a network of meaning rather than a collection of objects. Modern physics reveals a cosmos structured by informational relationships and mathematical code. This leaves us with the deepest question of all, the role of human consciousness within this informational web. If the universe requires observation to be actualized, we must ask why matter organized itself into minds capable of contemplating existence. Biology explains evolution, and physics explains fields, but the subjective experience of consciousness, to love, to remember, to wonder, remains unexplained by equations. Human beings function as active participants within reality, inextricably linked to the universe they observe. Every answer uncovers a deeper horizon. We find ourselves in a cosmos that grows more complex the more we know, held together by a mathematical structure we are only beginning to decode. In the next episode, we look at the numbers beneath it all,